Good morning to all of you. So, uh, so now we have learned both the Raman and IR spectroscopy, and also we have also we can now apply both the things together. Looking at the IR and Raman spectra or the spectral data, you should be able to now deduce the structure. So, uh, यही चीज़ कल हमने सीखा था लास्ट क्लास में कि हाउ यू कैन if suppose the data is given, looking at the polarized uh, Raman lines data, the IR data and the PQR branching, then you look for the Raman lines, appearance of Raman lines, whether it is polarized or depolarized, and looking at all these aspects, you should be able to reduce the structure. Okay, and in this context we had analyzed the simple one N2O in the last class. And one thing, whenever you are given a set of data, you can few things you can very easily pick up. Low energy vibrations, bending. Higher energies, uh, stretching vibrations. Amongst the stretching vibrations, the asymmetric one will be even the highest. And so we can easily point out here without looking into much of the details. ठीक है, सो तीन दिया हुआ है. अगर N2O मॉलिक्यूल है तो उसमें ये मुश्किल नहीं है फाइंड आउट करना कि कौन क्या होगा. देख के पता चल जा रहा है क्या है. बाकी सब चीज़ें डिटेल दी हुई हैं, अच्छी बात है, वो कंफर्म करता है फर्दर. बट प्रिलिमिनरी इन्वेस्टिगेशन आपको आइडिया तो लग जाता है कि 589 वाला बेंडिंग है और बाकी दोनों स्ट्रेचिंग मोड्स के हैं. तो एक सिमेट्रिक का होगा, एसिमेट्रिक का होगा. एसिमेट्रिक वाला हायर वाला होगा तो 2224 वाला एसिमेट्रिक हो गया, 589 वाला बेंडिंग हो गया, ये वाला सिमेट्रिक स्ट्रेचिंग हो गया बीच वाला. ठीक है, बाकी की कहानी तो आप इसमें कर सकते हो कि पी क्यू आर ब्रांचिंग. सो rest of the things we had discussed in the last class, so I think you will do good to go through that. So whenever it's a N2O type molecule, AB2, AB2 type molecule, N2O is one of them. So the possibility is both linear, non-linear structure, and so we can draw four such structures. But we note here the important point to be noted is that we have there is no mutual rule of exclusion followed. There is no center of symmetry. So the first you can rule out this the first one NON, which has center of symmetry. PR branches appear in all the three IR bands, but Q branch in only one. So no, so molecule is linear. It is not having a Q branch in the in parallel vibrations. Molecule is has no center of symmetry, and when there is no Q branch appearing in one of the in the parallel vibrations, you can clearly say that the molecule is linear. So दो चीज़ें आपकी बहुत क्लियर हो जाती हैं, और इसलिए ये भी गया, ये तीन स्ट्रक्चर गया. सो दिस इज माय स्ट्रक्चर. दैट्स हाउ वी अंडरस्टैंड दिस थिंग. ये लास्ट क्लास में हमने किया है. Okay, बाकी चीज़ें. So you can assign the bands. 589 centimeter inverse bending, that is associated with the least um, change in the polarizability, and theoretically it is Raman active, but may not be observable in the spectrometer because polarizability change is very small. So that this happens in case of water also. मैंने पहले भी कहा था कि वाटर का एक पीक या दो पीक ही कई बार दिखता है. It is difficult to see. The bending mode is usually very weak to be observed. Rest of the things we have already assigned to symmetric and asymmetric modes. Okay, then you also observe the polarized depolarized thing. What does this mean? This means that it, if the line is polarized, Raman lines are polarized, that means it must be a symmetric vibration. Or if it is partial, one is partially polarized, another one is is showing complete polarization. Then also you are moving to a greater symmetry. More polarization of the Raman lines, that means that particular vibration is symmetric, and greater is the symmetry, greater is the extent of polarization. That is what we can say. So depolarized and polarized, two distinction made. So that also further confirms that what you have been thinking is right. And asymmetric mode is okay. So this one I left it as an exercise. I will soon give you an assignment to on based on this kind of thing, combined IR and Raman. How can you predict? Okay. And in that context, we had also discussed the planar and pyramidal AB3 type molecules of both type. So the main observation was that in case of pyramidal AB3, all all the modes are Raman active as well as IR active. But in case of AB3 planar, you can see that there is one mode which is either only Raman active or only IR active. So you can see this particular one, this is Raman active only, and this is IR active only. So and other two are active in both Raman active, IR active, Raman active, IR active, like that. So obviously most symmetric vibration strongly Raman active, and more symmetric vibration will also be polarized. Amongst the Raman active vibrations, the one which is more symmetric, that will be likely to be polarized, and Raman active modes which is less symmetric, uh, if that is the case, then although Raman active, it may be depolarized, like that. Asymmetric stretching, Raman active, weakly Raman active, and it is also depolarized. So these are things that we have to look for whenever you are given this kind of data or spectrum is presented to you. You can always do these things. ठीक है, तो ये ज़रूरी होता है, और यही चीज़ हमने यहाँ पे एज एन एग्जांपल वी हैव एनालाइज द नाइट्रेट एंड chlorate molecules. One is of course, as you can see, the first thing in planar and pyramidal. So nitrate and chlorate. Okay, similar to what we have just discussed. So only one of them is mu2, only infrared active. Mu1, mu4, sorry, mu4 is only Raman active. Sorry, not this one, this one, 1049. mu1 होना चाहिए, हाँ, mu1 is only Raman active, mu2 is only IR active. So overall, you are getting 3 bands in IR, 3 in Raman. In case all of them are active in case of chlorate. So this was the case. So it is a scattering based technique, and we have seen selection rules for vibration. So so far we have discussed all this vibration Raman, that is Raman scattering, which involves the change in vibrational state of the molecule. So that is, so if you are having an incident green laser, the scattered beam, some of the radiations have changed in energy. That is red one, you can see red arrows that you see. So that is for the change in energy in the scattered radiations, and that change in energy correspond to the change in vibrational levels for the molecule. So the mechanism and everything that we have seen, Stokes and anti-Stokes lines, and so this is the classic thing, that the arrangement of the system. So this is a laser beam that is going through the sample, and then in a at 90-degree angle, usually we avoid the direct viewing. See, the scattering will occur in all possible directions, but usually you collect the data in where you have minimum background. So अगर आप डायरेक्ट 180 डिग्री पे डिटेक्टर रखते हैं तो आपका जो इंसिडेंट फोटोन है वो भी आएगा ट्रांसमिटेड ट्रांसमिट होके. So we usually view at 90-degree angle or any other such angles, which is to avoid the transmitted radiation as much as possible. Okay, because फिर वो आपको दिक्कत करेगा. And you have to apply a filter because Rayleigh scattering will always dominate. Rayleigh scattering is more dominant by a factor of 10 to the power 7, है ना. तो मतलब 1 करोड़ टाइम्स वो ज़्यादा स्ट्रॉन्ग फिनोमेना है जो होता है. तो इसको ऑब्जर्व करने के लिए आपको जो इंसिडेंट रेडिएशन है उसको ब्लॉक करना होगा. जो इंसिडेंट रेडिएशन की जो फ्रीक्वेंसी है उसको ब्लॉक करेंगे और जो चेंज इन फ्रीक्वेंसी उसको ऑब्जर्व करना है. सो दैट्स व्हाट वी डू बाय अप्लाइंग अ फिल्टर, ब्लू फिल्टर को. सो दैट इज ब्लॉकिंग दिस थिंग. Band rejection filter is applied, and then you see the change in colors, so to yellow. So this is how this is. So the longer wavelength, which is less longer wavelength photons, less in number, are observed uh, when you do this thing. So as I told you, the benzene was the first Raman spectra that was taken was for benzene. That's the thing. So now, so if you use so the laser I that is usually visible laser or near IR laser can be used. The example that I'm showing over here is for you can see this is the benzene spectrum. Raman, so what is plotted on, ध्यान दीजिएगा, what we write on the x-axis is the Raman shift. Why shift? Because it's the shift in the frequency of visible or near IR light. जो फोटोन है विजिबल लाइट यूज करेंगे या उसकी फ्रीक्वेंसी में जो चेंज आता है दैट शिफ्ट. सो जैसे यहाँ पे येलो ग्रीन से येलो हो गया और इस पिक्चर में ये ग्रीन से रेड हो गया, तो ये जो फ्रीक्वेंसी में शिफ्ट हुआ उसको हम नोट करते हैं. एंड दैट गिव्स अस आइडिया अबाउट द vibrational transition that is happening in the molecule. So that is, so in absolute terms you are taking this laser which is at around 9400 cm inverse. So that is your the change. If you and by what amount it has changed, the new photons that are observed have 84 shift at 8400. This is here, or at this is the CM inverse. So difference of the two is 1000 here, 3000 here, CM inverse, and this is exactly. So this is how it has been calculated. ध्यान दीजिएगा, एब्सोल्यूट टर्म्स में नहीं डिफाइन करते हैं. एब्सोल्यूट टर्म्स में ऐसे आएगा, जो जीरो है वो 940, नो चेंज नो शिफ्ट, तो ये जीरो हो गया. ये रिले स्कैटरिंग वाला पॉइंट है. जीरो जहाँ पे लिखा है ना वहाँ पे बहुत हाई इंटेंसिटी होगा रिले स्कैटरिंग, उसको हम ब्लॉक कर देते हैं टोटली फिल्टर लगा के. ठीक है. So we observe only, so we apply a filter which blocks the entire 1064 light. So scattered radiation में उसको ब्लॉक कर दिया हमने, और अब जो ऑब्जर्व करेंगे वो बाकी सारी रेडिएशन होंगी जिसमें चेंज इन एनर्जी होगा, चेंज इन वेवलेंथ होगा. तो इस तरह से हमारा रेमन स्पेक्ट्रम आता है. दिस इज हाउ वी अराइव एट रेमन स्पेक्ट्रम. So you can see wherever there is change maximum. So what is, you can clearly see what is this, ये इंटेंसिटी है. इस डायरेक्शन में जो आप देख रहे हैं वो इंटेंसिटी है, इंटेंसिटी वर्सेस द शिफ्ट. So that is, so what is most intense signal that you are getting is the ring, ब्रीदिंग मोड ऑफ द रिंग. सोचिए रिंग पूरा पूरा का पूरा एक साथ एक्सपैंड कर रहा है बाहर की, सारे एच एटम्स बाहर मूव कर रहे हैं, कार्बन एटम्स मूव कर रहे हैं बाहर की तरफ, maintaining the same structure of the molecule. There is no change in geometry of the molecule, but there is change in the size of the ring, like the lung contraction and expansion of the lungs when you breathe in, breathe out. So उस तरह का अगर दिखता है उसी को हम breathing mode कहते हैं. So this is the breathing mode of the ring at 992 cm inverse, and you also see an intense line over above 3000. So this is around 1000, एक हजार के आसपास दिख रहा है, और जो यहाँ पे आपको दिखा, और दूसरा आपको 3000 cm inverse के आसपास दिख रहा है, which is 3063 ch vibrations है. ठीक है, ch vibration at this thing. So these are the modes of vibration which involve maximum change in molecular volume. Molecular volume change होगा तो maximum change in, you are having a more spread out and contracted electron cloud. एक बार जब एक्सपैंड कर रहा है तो इलेक्ट्रॉन क्लाउड फैल जा रहा है, डिस्टॉर्ट करना इजी हो जा रहा है. उसी तरह से जब कॉन्ट्रैक्ट करेगा तो कॉम्पैक्ट, देयर विल बी कॉम्पैक्टनेस, सो द डिस्टॉर्शन विल बी इवन लेस इन दैट केस. एक बार बहुत ज़्यादा हो जाएगा, एक बार बहुत कम हो जाएगा. सो चेंज इन पोलराइजेबिलिटी जब आप कैलकुलेट करेंगे, दैट विल बी ह्यूज, एंड सो इट विल बी greater is the change in polarizability, greater is the intensity. इंटेंसिटी का सीधा लिंक जब आप रमन स्पेक्ट्रोस्कोपी कर रहे हैं, सीधा इट इज लिंक टू पोलराइजेबिलिटी. पोलराइजेबिलिटी इज लिंक टू हाउ द इलेक्ट्रॉन क्लाउड इज, इफ इट इज टाइटली हेल्ड, लूजली हेल्ड. तो हमेशा ध्यान रखिए कि अगर मॉलिक्यूल का वॉल्यूम देखिए, अगर बहुत ज़्यादा चेंज हो रहा है तो डेफिनेटली वो रमन एक्टिव होगा और स्ट्रांगली रमन एक्टिव होगा. सो ऑल ब्रीदिंग मोड्स, जैसे लंग्स का एक्सपेंशन कॉन्ट्रैक्शन होता है विदाउट चेंज इन शेप, जस्ट एक्सपेंड कर रहा है, कॉन्ट्रैक्ट कर रहा है, तो वैसा अगर चेंज जो हो रहा है वो सबसे ज़्यादा, that will be strongly Raman active, and that's what we see here. Breathing mode of the benzene. Aromatic CH is the next most intense line in Raman spectra. ठीक है, बाकी सब छोटे छोटे आ रहे हैं. So it is, and you understood how they have calculated. This is the 939 in the incident radiation, exciting light, lambda excitation, and it appears at a distance 992 cm inverse. So which is 8407, this is where it appears. So stretching mode is appearing like this at what cm inverse. CH stretching is appearing at this CH stretching mode. So we can just like to tell you something. Yeah, so just a moment, I will. कहाँ गया? हाँ, so we are talking about benzene, right? So this is a good website from chemistry department of Purdue University, and you can see the all modes of vibration have been simulated. ये simulation के through, computer simulation के through, ये सारे modes of vibration दिखाए गए हैं. You can see the entire modes that is possible in case of benzene. इतने सारे मोड हैं, और हमने कौन कौन सा देखा? 992 के आसपास बहुत इंटेंस रमन एक्टिव मोड देखा. So that is, where is that? Breathing mode. Breathing mode of vibration, Raman active. So one of them is here. Maintaining the center of symmetry. These two are the things, so around 900 something. और ये जो CH वाला था 3000. So you can, so calculation may differ, so it's slightly different position they are showing, but all those vibrations are also shown over here. Strongly Raman active CH vibrations. These are the ones, CH vibrations. CH. It is moving, Raman active mode, like that. So, so this is what, how does the Raman spectrum looks like. So there are some more molecules for you to have a look. How does the spectrum looks like? And these, some of these spectra may be presented to you for further analysis. ठीक है, कि इसमें क्या आपको दिख रहा है, या तो टेबल बना के आपको दे देंगे, या फिर आपको ऐसे करेंगे, ये देखो दोनों स्पेक्ट्रम दिया हुआ है, अब बताओ ये कौन सा मॉलिक्यूल हो सकता है, क्या इसमें फंक्शनल ग्रुप प्रेजेंट हो सकते हैं. So this is how you should be able to deduce the structure. So this is example of cysteine. सिस्टाइन होता है एक एमिनो एसिड, जो यहाँ पे फार्मूला दिया हुआ है, मॉलिक्यूलर फार्मूला यहाँ पे दिया हुआ है, आप देख सकते हैं. अब इसमें आपको दिख रहा है कि यहाँ पे जो ये वाला आई आर है, this one is IR and this one is Raman intensity on y-axis. Here it is the absorbance spectra, absorption, infrared absorption. This is the percent T, negative peaks are the, in terms of percent transmittance is shown over here, and this is the scattered intensity of the scattered intensity, right? इंटेंसिटी तो रमन स्कैटरिंग को इसमें इंटेंसिटी स्लाइड उसको दिखाएगा. सो व्हाट यू ऑब्जर्व, यहाँ पे जो था NH वाला पीक ज़्यादा डोमिनेट कर रहा है IR में, ऑफ कोर्स, ठीक है. बट जो so in case of IR spectra, it is the NH2 peaks which is dominating the IR spectrum. NH2 appearing on the higher energy side, dominating over here, और 2800 to 3200 के बीच में जो दिख रहा है वो यहाँ पे. So this one is corresponding to CH vibrations. CH दो पीक दिख रहा है ना, एक CH के लिए है और दूसरा CH2 के लिए, CH2 एंड CH, ठीक है, दोनों के लिए आपको दिख रहा है. So you can see these are the peaks that appear for CH2 CH vibrations, and NH3 plus deformation and carboxylic antisymmetric vibration. So जहाँ पे, so NH vibrations involve change in dipole moment, strong they are so they change in polarity, dipole moment changes, and that is strong. So we have already discussed, we know now कि IR, for a molecule to be IR active, there must be a change in the dipole moment during the vibration. NH has a greater change in dipole moment, so it is really strongly active in IR. That when we say मतलब उसका interaction, NH vibrations का जो interaction होगा, जो dipole generate होगा, उसका they will be interacting in a better way because the magnitude of the dipole is high. Stronger is the dipole, better is the interaction with electric field, oscillating electric field, और ये strong absorption वहाँ पे दिख रहा है. इसी तरह से कार्बोक्सिलेट का भी आपको बहुत इंटेंस पीक वहाँ पे दिख रहा है, जहाँ पे 1600 के आसपास. Carboxylate asymmetric vibration is more active. COH asymmetric at around 1600, very intense band. So polar groups देखिए, जिसमें पोलैरिटी का चेंज ज़्यादा डाइपोल मोमेंट से रिलेटेड है, वो IR में स्ट्रांगली एक्टिव दिख रहा है. और जो CH बॉन्ड है जिसमें डाइपोल में उतना चेंज नहीं है बट पोलराइजेबिलिटी इज सिग्निफिकेंट, सो CH and CH2 change in polarizability, that is polarizability changes significant. So polarizability changes significantly, but for these things, NH2 and COH, we have change in dipole moment. So these two peaks clearly are more active in IR, and the ones which are less, you also see the SS. Look at this thing, the central one is SS, which is again won't be showing a change in dipole, but when the two stretching and compression of the SS band will change, have a very strong change in the polarizability. There will be change in the molecular volume around that area, and that will be causing easy distortion or when it is stressed. So SS stretching is again, so SS stretching band which we see here also very strongly active in Raman for at 400 cm inverse, around 410, yes. So you observe these things. So clear hai, CH2 strongly active in here, in this part of the region, in Raman spectra. NH2 or COOH, that is carboxyl groups, they are strongly, these vibrations are strongly active in IR. The intensity will be high, so it is percentage negative transmittance that we are seeing over here. Like that. Okay, so so more examples I can present to you. So the thing to be observed, you can very easily see, this is a methyl ester of oleic acid. Oleic acid has a double bond and carbon-carbon double bond in the middle of the structure, and it also has carboxyl ester. So COO, the ester group is here. So you can see, so in this ester, what do you see? There are 2 points बहुत interest जो arrow देके समझाया गया है वो क्या है? Carboxyl change in dipole, polar bond, this CC non-polar. तो जब ये CC वाला expand करेगा, contract करेगा, the dipole moment changes is negligible, but the polarizability changes would be high. So this is active in Raman. So ये Raman spectrum में clearly दिख रहा है. CO वाले में polar bond है, इसको अगर आप stretch करेंगे, compress करेंगे, there will be huge change in the dipole moment. So this is strongly active in Raman, sorry, IR. So it is strongly active in IR spectrum, whereas it shows a very small peak in Raman. Weakly active in Raman, weakly Raman active but strongly IR active. CO, the CO stretch. Whereas when you are talking about C double bond C stretch, this the change in dipole moment is negligible, so it is weakly active in IR but strongly active in, it is, so intensity will be high in the Raman spectra for CC vibration. Intensity will be low, very very low, almost negligible, and sometimes it may not be, you may not be able to observe in IR spectra. So these are the crucial points that you look at first, कि point of difference कहाँ पे आ रहा है, ठीक है. So ये सब आपको समझना आ जाएगा, तो फिर आगे it becomes much easier how you find this. So this is the result. These are the summary of various peaks in IR and Raman that you usually encounter uh, in simple molecules and the functional groups. CH3 symmetric stretch around this frequency, very strong in IR, very strong CH3 symmetric. VS means very strong, M means medium, S4. So ये देखिए, this is the very strong, medium, weak, dash means absent. This is the mnemonics that we have followed. Now CC stretching, frequency expected is in this range, not active in IR but strongly active in Raman. Cyclopentane ring breathing always very strong in Raman, जो मैंने अभी बेंजीन के बारे में बताया, पोलराइजेबिलिटी चेंज. OH मीडियम, OH स्ट्रेच, अल्कोहल का जो OH होगा, this dipole change, so it is IR active but very weak in Raman. CH bending mode in acetylene at this particular frequency, strongly active in IR and weakly active in Raman. Acetylene CC bond, again you can expect to be C triple bond C, strongly active in Raman. So intensity will be high. CN bond in cyanide, strong change in, so it is a polar bond, polarity dipole moment changes are high, so strongly IR active. Along with dipole changes, when the stretching happens, there is also change in the molecular volume, and so it is also simultaneously strongly active in Raman. So ऐसा भी हो सकता है कि कुछ functional groups ऐसे भी होंगे, कुछ situations ऐसी भी होंगी जहाँ पे रमन एक्टिव भी होगा और स्ट्रांगली आईआर एक्टिव भी होगा. ऐसी भी सिचुएशन है जो यहाँ पे हम एग्जांपल देंगे. वेरी स्ट्रांग इन रमन, स्ट्रांग इन आईआर. साइनेट टी सी ट्रिपल बॉन्ड एन. सो अब देखिए सी ट्रिपल बॉन्ड एन साइनेट में भी होगा और साइनाइड में भी होगा. सो अकॉर्डिंगली the frequencies might change due to the local environment. CH vibration in aldehydes, you can observe it in this but not in this. So like this you have a series of things: NO2, symmetric, asymmetric stretch, asymmetric and symmetric stretch. Very strong in IR, medium to weak. Symmetric stretch very strong in Raman. जहां पे भी सिमेट्रिक स्ट्रेचिंग आएगा वेरी वेरी स्ट्रांग इन रमन. ये आप एक रूल ऑफ थंब ले सकते हैं. एसएच सिमेट्रिक स्ट्रेच थायोल्स का अगेन वेरी स्ट्रांग इन रमन, strong peak like this. So this is SS stretching bond जो जब SS सल्फर लिंकेज होगा ऑक्सीडेशन होने पे, so that is also strong in this like this. So Raman active, then halides, primary alkyl halides, iodide, bromide, chloride. The stretching vibrations strong, sorry, strong in this. So all of three will have dipole moments. So all these are strong in IR. They are also good in Raman. They will show good intensity in Raman. Change in polarizability associated with iodine Ri bond will be much more, and that's why it's very strong. You can see this as compared to RCl. It is strong, but it is very strong. Ri bond. So these are few things, few examples of Raman spectrum that we have discussed and where the frequencies will appear. Now, so it was all about vibrations. We had focused our discussion so far only on vibration. Now we move to the other part, that is rotational spectroscopy. Rotational spectroscopy, तो जैसे H2 मॉलिक्यूल रोटेट कर रहा है, N2 रोटेट कर रहा है, तो you cannot have any idea about that rotation through microwave spectroscopy, right? Pure rotational spectra cannot be observed in diatomic molecules, right? Pure rotational spectral in the conventional microwave spectroscopy cannot be observed. But because there is no permanent dipole there, तो dipole changes है ही नहीं involved उस केस में during the rotation. But there is change in polarizability in those molecules. If you are looking at the polarizability ellipsoid, which is elliptical, and as the molecule rotates, there is change in the polarizability direction of the डायरेक्शन. हाँ, सो इलेक्ट्रॉन क्लाउड का जो एलिप्स जैसा व्यू है वो पूरा चेंज होने लगता है. सो दैट इज पॉसिबल. So what we have already discussed the anisotropic polarizability in hydrogen molecule while discussing the ellipsoid. So we had, मतलब अगर H2 molecule है, So you expect, so this is your nucleus of हाइड्रोजन, 2 न्यूक्लियाई हाइड्रोजन हाइड्रोजन, और ये आपका व्यू ऑफ द इलेक्ट्रॉन क्लाउड होता है ऐसा. So this is my hydrogen atom, hydrogen nucleus, and this is the electron cloud. So polarizability when you apply electric field in this direction can be greater distortion. So more polarizable, it is more polarizable in this direction as compared to, and when you apply electric field in this direction, less polarizable along this. So this is what we mean by saying that it has anisotropic polarizability. In terms of polarizability, ellipsoid, you draw it like this, or I mean in the reverse case, because 1 by alpha more polarizable, smaller axis, high polarizable. So that will, when you draw this axis, it will be like a ellipse. माइनर एक्सिस इन दिस, ये रिवर्स जाता है, ठीक है, और ये मेजर एक्सिस, मोर पोलराइजेबल माइनर एक्सिस and less polarizable represented by, so because it is 1 by under root alpha is your scale through which we draw this thing. चलिए, तो ये चीज, so a simple, the simplest molecule, that is hydrogen molecule, is having, we have learned that it has anisotropic polarizability. So anisotropic polarizability is an essential condition for a molecule to show rotational Raman. Pure rotational Raman spectra can be observed only if the molecule has anisotropic polarizability. So in this, we have already derived equation for vibrational Raman. In the same way, you can account for the, you can write the equation for uh, rotational Raman. Here we have to look for the rotational frequency, incident frequency of incident light, frequency of scattered light. So इस दोनों को आप ऑब्जर्व करते हैं, और ये जो सॉरी, फ्रीक्वेंसी ऑफ स्कैटर्ड लाइट तो ये होगा, फ्रीक्वेंसी ऑफ रोटेशन होगा ना, रोटेशनल फ्रीक्वेंसी, ठीक है, और ये दोनों मिला कर ये जो फ्रीक्वेंसी ऑफ इंसिडेंट लाइट, ये जो म्यू माइनस म्यू है, ये दिस टोटल थिंग इज द scattered light की जो frequency होगी, वो म्यू नॉट माइनस म्यू रोटेशनल. So that much energy has been used up in promoting the, in exciting, in the rotational excitation of the molecule from the lower state to higher. And in the other case, this has been used in the molecule, the energy of scattered light has increased. In this case, increased energy or frequency of scattered light has, okay, so this is your again it is Raman scattering, but is anti-Stokes. So this is the thing that okay, so this, in we can form a similar equation as we did for Raman vibrational spectroscopy. In rotational spectroscopy, the only difference is that in the scattered radiation there will be small difference due to this change in the frequency. So the rotational excitation or de-excitation may occur, and that energy may be represented through in the scattered light. So the photon energy increases if it is this one, the blue one, and it will be the photon energy will be less if it will be if it is goes from J0 to, like, let's say J0 to J1, or here I mean J0 J2 to, अभी हम देखेंगे मैंने यहाँ पे 2 लिखा है प्लस there is a difference in the selection rule for rotational Raman and selection rule for previous we have seen delta J plus minus 1 होता था, यहाँ पे 2 क्यों होगा ये आपको अभी अभी हम लोग डिस्कस करेंगे थोड़ी देर में. चलिए, so this is the basic equation that remains same, only that we have replaced the rotational vibrational frequency with the rotational frequency. Okay, and we get the entire Stokes and anti-Stokes lines. We can account for their frequencies, and so rotation, if it is a spherical top molecule, the rotation have it will not be Raman active. So Rayleigh scattering. In the Rayleigh scattering, the induced dipole oscillates with the frequency mu naught, same as the incident radiation. In Stokes scattering, the induced dipole oscillates with frequency either this or this, increase or decrease in frequency. So this is the example of your molecule. Say we have this one is hydrogen and this is chlorine. So HCl. So suppose this is my HCl molecule. Suppose you have HCl molecule and then it is moving like this, है ना, ऐसा हो रहा है आपके साथ. So it is moving in a this way, anti-clockwise fashion. और फिर ये Cl इधर, H इधर, फिर और एक बार टर्न करो तो H ऊपर चला जाएगा, Cl नीचे आ जाएगा, ऐसे करके it is continuously moving. So do you realize this that so अब ध्यान से देखिए, if it is HCl molecule rotating like this, look at the change in the polarizability. Polarizability changes कैसे हो रहा है? So alpha electric field is direction of, so light is falling in this, going in this direction, and the electric field of the oscillating light is here. Sorry, the oscillating electric field in the light, if it is visualized at this arrow, E जो है, this is the electric field of the, so you are applying electric field in a constant direction. Suppose एक particular direction में, upward direction में electric field apply किया गया, and the molecule is undergoing rotation. So molecule is rotating. So when it is perpendicular to the molecular axis, so it is alpha perpendicular polarizability, and this is the alpha parallel polarizability is shown here like this. So in this case, you have the polarizability is shown by the yellow colored block. So you can clearly see that there is change in polarizability when it is perpendicular or parallel, and the cycle repeats. Polarizability का 180 degree के बाद, so you can clearly see, now you can visualize the thing, so it will be easy. So it is a HCl molecule, the black one representing chlorine and the white one representing hydrogen, H and Cl. So polarizability का प्रोफाइल देखिए, एक बदल गया, then it is at 180 degree, it is again repeating the same cycle completed, returning polarizability returning to original thing after 180-degree rotation. When you rotate by 180-degree, you are getting the same value of polarizability, and then again continuing the rotation 360-degree. So you are so it is equivalent of change in polarizability twice, two times. So one complete revolution, it is the polarizability is returning to its original value two times. It is like completing two circles, दो मतलब दो वेव के टर्म्स में. और इसलिए so this is one of the things that we have to understand. Whereas look at the dipole, however, dipole changes जो होगा, जो IR के लिए जरूरी है, उसमें कैसे हो रहा है, प्लस टू माइनस, this is the direction. So so polarize, यहाँ पे जो डाइपोल का डायरेक्शन है वो ऐसे चेंज हो रहा है, और डाइपोल इज रिटर्निंग. सो डाइपोल चेंजेस जो हो रहा है डाइपोल का, देखिए वन साइकिल इट इज रिटर्निंग टू इट्स ओरिजिनल वैल्यू ओनली आफ्टर 360 डिग्री रोटेशन. दो चीजें देखिए, द डाइपोल रिटर्न्स टू इट्स ओरिजिनल वैल्यू only after 360 degree rotation. The polarizability returns to its original value, initial value, only after 180-degree rotation. So when you are taking a one complete revolution, in that it polarizability changes are happening twice, and this is one of the reasons why we also have delta J. The change in quantum number in this case is plus minus 2. Another thing you can view is that we have seen that that figure, I think that figure should have been important here. There are two photons involved in this process, which I might just like to see here. Yeah, as we have seen in case of suppose this one. So one more thing is important here. You can see here there are two photons involved in the process. Photon 1 in the photon number 2. So Raman spectroscopy, it is two photon process involved. In Raman spectroscopy there are two photons involved, and each of these photons is photons are what? Spin 1 particle, that is for spin quantum number is given by s is equal to 1, and the angular momentum is under root s into s plus 1 h cross. This you know already, right? So अगर ये so energy changes, तो you are conserving the energy, fine. So the total spin also must be conserved. The angular momentum must be conserved. ठीक है? So to conserve the angular momentum, the overall change in the molecular rotation should also be same. So that's why if what is the angular momentum for the rotation? Angular momentum for rotation, molecular rotation, when the molecule is rotating, and if I ask you what is the angular momentum, how will you find? You should know the quantum number. J is the quantum number, J plus 1 h cross. So देखिए h cross तो constant है. If the change in J is same as the change in spin quantum number, then you are accounting for the change in overall change in the angular momentum. So two photons, since there are two photons involved in the process, each spin 1 particle, one particle, so each one having one particle, so which have under root s into s plus 1 h cross. So the overall change in angular momentum, इसका जो एंगुलर मोमेंटम है इतना है, दो फोटोन इन्वॉल्व है, दोनों का एंगुलर मोमेंटम कंजर्व करना है, सो जे मस्ट चेंज by 2 units. Then 2 photon process का आप पूरा का पूरा angular momentum conserve कर पा रहे हैं. So that's why we have, so because of this we have uh, the so to conserve the angular momentum, we have to change the angular momentum of the during the rotation by by the same unit, by the same magnitude. So the quantum number j must change by 2. So that's why you have delta j plus minus 2 is the selection rule for this thing, plus minus 2. Okay, delta j would be plus minus 2 for pure rotational transitions occurring in Raman spectroscopy. Okay, so two reasons why. Okay, so now you understand what. So because two photons are involved, each of them have spin quantum number as 1. The angular momentum is given by this s into s plus 1 h cross. So you sum up the two angular momentum. The change in angular momentum for the molecule should be the same during the rotation, and therefore the j also must change by 2 units. So delta j, so to conserve the angular momentum, the delta j also j changes by 2 units plus minus 2. So इसीलिए delta j plus minus 2 होता है. ठीक है, we have already discussed this slide should have come first. I think the arrangement is slightly here problem. So electric field, so we have discussed this earlier. Change in polarizability, and so this kind of thing. So here what it is shown in the diagram is that you apply electric field in this direction, you have polarizability given by this. When you apply in this direction, that polarizability is different, and so we call it, this type of molecule is having anisotropic polarizability. And for example, in hydrogen molecule, this is the case. Alpha parallel is greater than alpha perpendicular. This is shown over here. So all linear molecules and diatomic molecules have anisotropic polarizability, and so all of them are rotational Raman active. All linear molecules, all diatomic molecules, है ना, homonuclear or heteronuclear, so all of them will be Raman active. Rotationally, pure rotational spectra can be observed in these cases. ठीक है, so this is the only technique by which you can obtain the rotational spectra for such molecules, homonuclear diatomic molecules, जिसमें कि पहले कोई ऐसा कुछ था ही नहीं, possibility नहीं थी. Okay, so these molecules were inaccessible. We say that these were inaccessible by microwave spectroscopy. The rotational data was inaccessible but by performing Raman spectroscopy, rotational Raman, it is possible. ये बहुत बड़ा contribution है रमन का, कि एस बी अब कितना important था रोटेशनल कांस्टेंट डिटरमिन करना, बॉन्ड लेंथ उसी से निकलता है, और वो हम कर ही नहीं पा रहे थे किसी भी होमोन्यूक्लियर मॉलिक्यूल के लिए. और ऐसा कोई भी जो लीनियर मॉलिक्यूल था जिसमें परमानेंट डाइपोल मोमेंट नहीं था, उसमें भी नहीं हो पा रहा था. लाइक CO2, नो परमानेंट डाइपोल मोमेंट, no, it was microwave inactive. So how do you do that? You again perform rotation in the Raman spectra. If you observe a change in the rotational lines, rotational transitions can be observed, and you can, spherical rotors such as CH4, SF6 are Raman inactive. There is no permanent dipole. The polarizability ellipsoid is also symmetric. So that is, they do not have anisotropic polarizability. They both have isotropic. They have isotropic polarizability, and so they are inactive. Raman inactive. So far as Raman spectroscopy for these molecules you can't do. अभी भी एक दिक्कत रह गई. सब रमन में सारे इंक्लूड हो गए. डायटोमिक होमोन्यूक्लियर डायट तो एक्टिव है, बट ऐसे मॉलिक्यूल्स के लिए अभी भी देयर इज नो होप. होपलेस सिचुएशन होती जा रही है कि अब इनका कैसे किया जाए रोटेशन डेटा. बट होता क्या है कि they are found to be excited. These molecules are found to be excited in a rotationally excited state in a different way. अगर आप मॉलिक्यूल्स को कोलाइड करते हैं एक दूसरे से तो तब भी एनर्जी ट्रांसफर होता है. वो एनर्जी रोटेशनल मोशन को चेंज कर सकती है. हीटिंग करते हैं तब भी हो सकता है. हीटिंग से ही तो कोलिजन होगा. सो मॉलिक्यूलर कोलिजन्स कैन चेंज द रोटेशनल स्टेट ऑफ वन ऑफ द अदर मॉलिक्यूल्स. तो हीट करके आप उसको चेंज करा सकते हैं. सो दैट इज द ओनली वे. बट लाइट के एब्जॉर्प्शन से नहीं होगा कोई. किसी लाइट के एब्जॉर्प्शन से क्योंकि माइक्रोवेव इनएक्टिव भी हो गया और रमन इनएक्टिव भी है. सो इट इज स्टिल डिफिकल्टी. हम उनके बारे में अभी भी नहीं कुछ कर सकते. सो रोटेशनल रमन सिलेक्शन रूल्स डेल्टा जे प्लस माइनस 2 होगा. दैट इज इम्पोर्टेंट. डेल्टा जे जीरो ट्रांजिशंस को यूजुअली हम नहीं कंसिडर करें. दैट इज नॉट अ प्योर. दैट मीन्स यू आर टॉकिंग अबाउट when delta j is 0 there is no change in the rotational state. So ये तो इक्विवेलेंट ऑफ रिले रेडिएशन रिले स्कैटरिंग हो गया. सो रोटेशन में अगर कोई चेंज नहीं हो रहा, डेल्टा जे 0 है, दैट इज इक्विवेलेंट टू रिले स्कैटरिंग. सो रमन स्कैटरिंग के लिए जब भी हम लिखेंगे तो प्लस माइनस 2 ही लिखेंगे. लीनियर रोटर्स. सिमेट्रिक रोटर्स again. So for the Raman spectrum, a linear rotor will apply that selection rule is delta j plus minus 2, and the scattered radiation. So when a molecule makes a transition, higher excited state में जाएगा, 2 यूनिट का चेंज होगा. J will change by 2 units. In a higher rotational state, the wave number incident radiation is decreased mu I. So you can write this form. So you know the rotational description. We have learned it in microwave spectroscopy in terms of J. J changes by 2 units. So J into J plus 1 initial. This is your initial state. Initial, and this is the final. So J को हमने चेंज कर दिया. So J to J plus 2. ये देखिए J to J plus 2 का चेंज है. So accordingly Vj into J plus 1, you get these values. So the formula is incident radiation. इंसिडेंट लाइट की फ्रीक्वेंसी है and minus V into 4j plus 6. So that is where you will observe the so this is the change in the frequencies. So this is the frequency of the light that will be observed in the scatter when rotational transition has happened. So a pure rotational spectrum looks like this. So Vj minus so anti-Stokes line in this side, and इस side में वो उतना. So Stokes line decrease in the intensity and decrease in the frequency, and on this side it is the increase in the frequency, anti-Stokes line. So corresponding to transitions you can see for each of these transition it has been shown. So वही profile है जैसे कि population of states, degeneracy of each levels, वो सब काउंट करेंगे तो बीच में आता है जो हमने पहले डिस्कस किया है, प्योर रोटेशनल स्पेक्ट्रोस्कोपी जब पढ़ा था, माइक्रोवेव स्पेक्ट्रोस्कोपी। सो बीच में कहीं पे मैक्सिमम आता है ऑन दिस लेफ्ट हैंड साइड. दिस इज द रेले लाइन that we observe like this. Things would be so overall effect. So because delta J must change by 2 units, सेंट्रल लाइन से 6b इधर और 6b इधर चेंज आएगा, and the separation between the line will be 4b in each case. So rotational Raman appears, Stokes line will appear at lower frequency 6b, 10b, 14b for when you consider J0, 1, 2, and the molecules make a transition. Yeah, so Stokes line, lower energy for the photons. Anti-Stokes line, the scattered photons will have higher energy and there will be de-excitation. And anti-Stokes line will occur at displacements of okay, so in case of, so एक बार यहाँ पे जो हम देख रहे हैं photons, ये Stokes है, Stokes line, anti-Stokes on this side, increased frequency of scattered light, and on this side it is the decreased frequency for the scattered light. So excitation, यहाँ पे आप पिक्चर में देख रहे हैं, going to higher J levels, and on this anti-Stokes line it is going to the lower J levels. So you can clearly see these things happening here. So that's the thing that is written. Separation of lines we have already seen, it is 4p. And then we should be able to, when you perform this measurement, 4b निकल गया तो b निकल गया, rotational constant निकल गया, bond length निकल जाएगा. So it will be, so given a situation you should be able to calculate nitrogen. In the rotational Raman spectrum for nitrogen, laser used was this one, 336 nanometer. And what is the form of, predict the form of the rotational Raman spectrum if the B is this one. So अगर आपको दिया जाए to the scale drawing करने के लिए, बताने के लिए, तो solution आप कैसे करेंगे, इसको solve करेंगे. Molecule is rotationally active, end over end rotation is changes, polarizability will be there, nitrogen molecule just like hydrogen, and incident radiation, this corresponds to itna cm inverse 29,697. So Stokes and anti-Stokes line will develop with a change. You can calculate for anti-Stokes line that will appear with increase in energy 0 to 2, 1 to 3, 2 to 4, 5 to 3. So mu like this. And in a similar fashion you can calculate the anti-Stokes line. Anti-Stokes line will be in the reverse order, 2 to 0, 3 to 1. So this is how you can calculate, given the situation you can calculate the thing. So that's, it should be. So nuclear spin effects I have already discussed nuclear spin effect while discussing the rho vibrational spectroscopy. Please go through that lecture where I have discussed the nuclear spin effects, and I have also discussed the ortho and para hydrogen, the vibrations, the rotational transition in ortho and para hydrogen. So that thing is already discussed. Please go through that. And so that brings us to the end of this rotational spectroscopy. So polarizability, ellipsoid, we have already drawn this thing. So ठीक है, आज के लिए बस इतना ही. Thank you.